Hi everyone, I'm Naoum Mashraqi. My project is low-frequency shot noise spectroscopy to study superconducting mechanisms. My PI on this project is Laura Green. So what we did is we built a measurement scheme to perform shot noise spectroscopy in our lab. Shot noise spectroscopy can be used to study potentially novel states in a superconductor, and we were able to get some preliminary data on a superconductor to prove the feasibility of this method. So first, I want to define some things. So a superconductor is a conductor that performs lossless power transmission. The electrons in the superconductor buddy up into Cooper pairs, and so each Cooper pair has twice the effective charge of a single electron. Some superconductors have novel states that may be Cooper pairs and may not be Cooper pairs. So what this project aims to do is to develop a method by which we can determine if there are Cooper pairs in a novel state of a superconductor by measuring shot noise. So what is shot noise? Any fluctuation in current in a superconductor is shot noise. And any current fluctuation is noise. And shot noise specifically refers to charge quantization that induces noise that's induced by charge quantization. And this can be used to determine effective charge of the charge carriers. So what we did is we just took a simple resistor and did sample measurements on various resistors until the system's been calibrated. Then we measured noise in two systems, a lead thin film and a superconducting lead thin film. And we isolated the contributions that were a shot noise, and we took the ratio, and we were hoping to see that beautiful, beautiful number 2. So as for what we did, we built this circuit here in figure 2. All things considered, not the most complicated circuit, but also the most frustrating one I've ever worked with. We calibrated the measurement by measuring the thermal noise specifically, and we knew that the system would be calibrated once the measured thermal noise matched the predicted thermal noise. Once we got that, our measurement was calibrated, and we were able to measure the total noise on lead thin films in our physical property measurement system, or PPMS. And we swept multiple variables, resistance, temperature down to superconducting temperatures, magnetic field, and current. And we used a combination of numerical and experimental methods to isolate the shot noise contribution, because in the total noise contribution, there are maybe 6 or 7 forms of noise, depending on what material you're looking at. So we had to isolate the shot noise contribution first. Then we took our ratio, hoping to see that number 2. So as for what we saw, we got something very close to 2, but obviously there's a lot of work that can be done. So what we did was we took something called an octave average. We separated our noise measurements into buckets, where each bucket had twice the width and frequency as the previous bucket did. And then we also just took our raw noise data, and then we took the ratio of that. So what we did was we took noise measurements in a superconducting lead film and a lead film that is not superconducting, and we did this by killing the superconductivity in lead with a magnetic field, so that all of the variables like temperature and resistance were the same. And what we saw was that when we plotted the noise, we get this weird trade-off. So at low frequencies, we don't see anything close to 2. But the measurements are pretty precise. And as we increase frequency, they average out to 2, or in this case, log 2, because it's a log plot, but we lose precision. So this is promising preliminary data, but there's a lot of work that can be done specifically with the measurement apparatus. We've discussed several ways of improving the measurement apparatus to increase precision. So, conclusion, we've had a few goals, and I would say we succeeded in most of them. So we supplied the ability for the lab to do shot noise spectroscopy at low frequency in the first place. This wasn't something that we were able to do 10 weeks ago. We were able to perform noise measurements on multiple systems, including on a thin film. I was very surprised that that worked. We were able to isolate the contribution due to shot noise, extract the charge of the charge carriers, and obtain preliminary data for a superconductor. Some things can be improved, like the technical improvements to instrumentation and improve external standard noise filters. We also discussed better shielding and better cabling. From here, all I can say is that there are more materials to do shot noise spectroscopy on. than thin films. So we'll get started on that ASAP. Noise spectroscopy is a good tool to study superconductors, and I think what we've did in this project is prove that the method is feasible. Right? Thank you.